So this is a brief outline of this presentation. So we're going to start with an introduction and my two projects based on two papers and conclusion. So for my introduction, I'm going to start by trying to explain some terms that are relevant to what we will be talking about today. We're going to be talking about things relevant to grounding, concepts, semantic knowledge bases, and language models. So what is grounding? Grounding simply means connecting language to perceptual experiences. And in this image here, we can see that we are trying to connect dog, the word dog, to the perceptual experience of the dog that you can see in that picture. And we are doing the same thing for grass. So why is grounding important? It's important because language is more than words. It's a tool that we use to express ourselves and to refer to things, whether real or imagined. And studying grounding allows us to connect language to things and perform other tasks above that, such as visual question answering. So in this picture below, we can see that when we have sufficiently grounded language to this picture, we can ask questions such as how many legs does the dog have in the air, or what breed of dog is this? And we are not able to sufficiently understand questions like this if we have not grounded properly. So what is a concept? This is something that most of us will know already, but it's just a formality. So a concept is just an abstract notion that generalizes a class of something. And you can see Scooby-Doo and a dog in glasses and a dog in a Louis Vuitton top. And when we see all these images, we have something similar that's is elicited in our brains, and that is the concept of a dog. And the concept is anything that represents something. So a semantic knowledge base is simply a repository of knowledge about concepts and relationships between them. So here we can see that we have like some root node, which is like an entity. Then as we go down, it gets more fine-grained. And we have here portable computer, and under portable computer, we have laptop and notebook, which are types of portable computer. And the relationship between portable computer and laptop is one of, and is a relationship because the laptop is a kind of portable computer. Same thing goes for alligator and crocodile. So what's a language model? It simply predicts the next word. So I thought this was a bit of a funny example, but I truly believe this is the greatest province in the world, even though that may not make sense geopolitically. But this is what we might expect a properly calibrated language model to say, but more practically, language models help us to produce contextual and coherent text. So now that I've spoken about all this, I want to talk about my thesis statements. I don't know if it's a good thing or a bad thing that my thesis statement can be summed up with a meme. So descriptions that focus on visual attributes of a concept do better on zero-shot visual language tasks. And zero-shot simply means you are not trained specifically to do this, and vision language simply means that the task requires knowledge in both modalities. So we can see that for this image of a brambling, which is a kind of bird, something that is a more typical definition would say something like Eurasian finch, and our visual description would say something like a small brown bird with a black head and a white patch on its chest. And what we're basically saying is that descriptions that are like this, as opposed to the first one, do better on tasks that are required to the tasks that require zero-shot vision language skills. So I'm going to talk about my first project. This was worked on a shared task. So the topic is context augmentation and translation for visual word sense disambiguation, WSD. So we're going to start with WSD, which is a prelude to the visual WSD task. So in traditional WSD, we have a focus word in context and we want to determine its sense. So this is an example. I would say something such as, I went to the bank to deposit some money and I would like to know the meaning of that. And it wouldn't be the edge of the river, rather it would be a depository financial institution. And this is simply the task. You map the word to the sense that's referred to in context. And we have a second task called visual WSD. So in this task, we have a focus word in context similar to the previous task. But what we are picking from is not a set of senses, but rather a set of images. So that's the difference. So this is an example. We have the focus word bats, we have the context baseball bats. And we have a couple of images that we're meant to pick from. One is an image of the baseball bat, which is of course the correct image. We have an image of a mammalian bat, we have an image of someone dressed up as Batman, and we have an image of several baseballs. And you can see that if you do not understand the context that bat is in, this becomes a very hard problem. Even with the context, it's sometimes a difficult problem. So what is the motivation of this project? The motivation behind visual WSD is to understand semantics when context is extended to images. And there are various applications for this, such as image retrieval, image captioning, and multimodal machine translation. So I'm going to give a brief background on some of the tools I've used, or one of the backbone models I've used, which some of us would have heard about. It's called CLIP, Contrastive Language Image Retraining. And with CLIP, we want to learn a shared representation of both text and images.
Excuse me, there are people on the web, on Zoom, waiting for the talk. So I came here to find out why is that this talk not online.
I can probably help you with that.
Yeah.
So we want to easily compare text and images. And that's what we are able to do when we have a shared representation for both text and images. So we can see this diagram here. And essentially, what the image encoder and text encoder want to do is to create vectors. And when we take the dot product of these vectors, we want to have something that looks like an identity matrix, essentially. So what is our method for solving the visual WSD task? So this task is multimodal. We have English, Farsi, and Italian. And the first thing we want to do is that for the non-English context, we want to convert them to English. We just translate them. And we see that because of how good multimodal machine translation models are nowadays, it's able to do this fairly well. And for context augmentation, which is the really important thing here, we pass in the context, which is baseball bat, and we ask our language model to produce text that describes the visual attributes of this. And we can see that it says things such as cylindrical and used to hit a baseball. So these are the visual attributes that we care about, and these are the visual attributes that allow us to understand the meaning of the baseball bat more concretely. So what is our method? Here we simply want to compare, well, our method has 3 components, and we simply want to pick the image with the strongest affinity to both the context and the senses of the focus group. So there are 3 components here. We want to compare context to the images that we have to choose from. We want to compare glosses or definitions to the images we have to choose from. And we want to compare the context as well to the glosses or definitions. And when we sum and normalize these in our algorithm, we get like a final probability distribution, and we simply take the argmax of this and get the image that is most similar to the context. So the baseline that we compare to is simply comparing images to text with monolingual models. So what this means is that we have a single model show that we have a single model that is able to understand both English, Farsi, and Italian, and we use that to compare to generate a representation for the context and compare that to the images. Since we are using CLIP, which encodes both text and images in a similar semantic space, this is an easy thing to do. The second method that we have, the alternative method, is to use language-specific models. And here we use English, Farsi, and Italian, like separate models of these, and we compare them separately. So we have our English samples going into a different place from our Farsi samples, and going into a different place from our Italian samples. I want to apologize because the images here are like this image refers to the previous slide and vice versa. So sorry about that. The second alternative method we have, which I think is quite a bit interesting, is that we try to generate an image from this context, and that image is what we compare to. So instead of comparing text to images, we translate the text to an image and compare images to images. And we see that this, we will see that this performs surprisingly well. So without further ado, our results. So the baseline, we see that it performs decently for English. The gen of which is image generation, it performs decently as well. We see that with the translation, that this uses translation for some of the samples, it does better. Surprisingly, language-specific models don't perform very well. That was a bit disappointing because you should expect that when you translate from one language to another, you get like some errors, and those errors actually cause you to perform worse. But it turns out that this is not the case, and when we translate, we do in fact do better because the English models are so much better than everything else. And that's what we see with our method, which is TR plus 1. So yeah, go ahead.
Sentences they are in different languages and the images remain the same.
Yes, but the images are sometimes more contextually relevant to the languages. So for example, an image with the Farsi sample might have something more related to Iranian culture.
I see. And what is the task again?
Visual WSD. So here you want to, I'm going to go back here, you have a focus word and you have some context, and based on the meaning of the box which is underlined, you want to pick up.
I see.
Yeah. I'm sorry, if anyone wants to ask a question, please feel free to interrupt. Okay, go ahead.
Sorry. So why do you think English outperforms the other languages?
There is a common phenomenon in NLP, which is like some sort of English language hegemony. And I think it's just that most of the data is in English. Most of the researchers are from America, which of course speaks English. And there's just a strong bias towards English. So much so that you can't do much serious work if you're not working on English.
But to follow up on that question, I thought you said that there's a caption for every language for each image. So then wouldn't that make the data set balanced?
No, so you have a set of data sets, right? And each data set has some samples. The data set has some samples that are English, it has some samples that are Italian, and it has some samples that are Farsi. There is no cross-lingual, it's just different languages.
Thanks.
Yeah, thanks.
Another question.
Yeah.
So you had one of these elements of image generator based on
Yeah.
text, right?
Yeah, exactly.
So do you have such generators for different languages, or do you first translate to English and then query the image generator?
Yeah, first translate to English.
Okay.
Yeah. And the image generator is Stable Diffusion, which many of us have used.
How do you compare the images?
So we use CLIP again. CLIP encodes both text and images in a similar semantic space, but it can also encode images, right? Because you expect the images to be close to each other
Right.
as well.
When you compare the vectors.
Yeah, exactly. We do normalized dot product. So what are the takeaways from project one? I see that context augmentation is very important, and we observe a 20% drop increase in performance across all languages. And yeah, that's it. Having a baseball bat is a cylindrical club performs surprisingly better than having just a baseball.
Oh, you said surprisingly?
Yeah.
Isn't it obvious?
Um,
Like, well, I'm not discounting any of the work. I'm
Yeah.
just saying, isn't this reasonable?
I mean, it is reasonable when you think about it. But the interesting things that we've done here is that we do it in like an automated way. And yeah, we do it in an automated way, and we get some information from WordNet. Yeah, which is, I guess, here. So the second set of takeaways is that, and this alludes to what Adrian spoke about, applying English-only multimodal models on translated context yields higher accuracy than language-specific models. And we see that Farsi or Italian to English outperforms directly working on Farsi or Italian. Yeah. Yeah, sure. So the online question is there a characteristic correspondence, like can it be independent of the color of the bat in question? Yes. So what we try to do here is that we don't want to describe things that are not general enough. We want to describe general attributes of like a bat. So we wouldn't say that a bat is black or a bat is white because a bat can be black or white. For a dog, we wouldn't say a dog is white or black because a dog can be multiple colors. So we want to focus on things that are unique visual attributes of the thing in question. Sometimes that extends to colors, sometimes it doesn't.
Is the reason why you want captions to be general is so that there's like some overlap between descriptions of objects in different languages? Or why do you want there not to be less specificity?
So we want less specificity because we want specificity when it's useful, but we don't want like too much specificity. We want to focus on what we are actually describing. So if we are describing like a dog in general, we wouldn't describe a color. But if we are describing something like a Dalmatian, we might want to say the specific color of a Dalmatian.
And how do you like get that balance? Is that just in the data set?
Yeah, so with WordNet, we have all that stuff, right? So you have different concepts and things like that, and we are able to draw the potential senses of each word from WordNet.
Is that WordNet for Farsi or Italian?
No, we translate.
Okay.
Yeah, we translate. Yeah.
So maybe this is a question from your related to your T10 talk.
Yeah.
Is that so sometimes these descriptions can have words which have like a negative connotation, right? Or something like a not there.
Yeah.
Are the image generators or something that you're using, do they suffer from that? Like, for example, I don't know, mosquito repellent, the description could be so that you do not have mosquitoes in your surroundings.
Yeah.
But if the image generator doesn't, like in your talk, you mentioned that this is hard for image generators to model. So perhaps you generate an image with a bunch of mosquitoes in your surroundings and you do a match and
Yeah.
do you have any of those issues here?
Yeah. Well, Clip isn't super great at encoding the meaning of text, but what we try to do in this project and the other one is that we sort of restrict the model from outputting words that could be confusing. So we don't want it to say what something is not, but we want it to say what something is instead. I think that with more powerful models, you are able to understand negation and composition and things like that better, but we don't use those powerful models. So, and please feel free to interrupt me more. So I'm going to talk about the second project now, and the second project is visually grounded descriptions improve zero-shot image classification. And these visually grounded descriptions are generated with a language model as well. So moving to the problem. So manually coming up with prompts is really time consuming, and bad prompts or descriptions lead to poor performance. So we can see this set of images. And with this crane image, there's a lot of ambiguity. You see a crane, sometimes you see a crane and a bird crane and a construction crane sometimes. And in the corner there, you see a construction crane that's supposed to look like a bird, which is, yeah, it's very funny. But that sort of alludes to some of the things Abhishek said, right? The models are not great at understanding meaning. And that's why augmenting them with sort of attributes that bias the meaning towards what we want improves performance so much. We see that when we have construction, we are able to control the model way more. It now shows consistently construction cranes. And when we have bird, it biases it towards generating what we want, and we have crane birds actually. So we can do this manually, but it's time consuming, and we can see the result of not having good prompts. So what is our goal here? We want to automatically produce better concept prompts or descriptions for vision language tasks. So instead of Gary here coming up with prompts himself, we can have a robot do it for him. So what is the task in this project? So the task, what we call this task is visual concept description. And what it simply is that given a class, we want to generate visual descriptions for that class. So for example, when provided with dog, we wish to produce a description of what the dog looks like. And again, we're focusing on visual attributes like we did before. And our hypothesis here is that descriptions that ground the concept to its visual attributes do better on zero-shot image generation and classification tasks. And that goes back to what I said earlier. When you sort of have related attributes in the context, you are able to form a stronger relationship with the description and what you're trying to describe. So what is the background work? So there is a method called template ensemble, which comes from the original clip paper. And here what they do is it's a straightforward method. They simply insert labels into templates. So you have something like a photo of a crane, an origami crane, or a rendering of a crane. And they come up with several of these templates, about 80, and they encode these templates and sort of use them to form an average meaning of each of the concepts. And there is a more recent method called QPO, which is customized prompting for language models. And what they do here is to instruct GPT with a phrase or a question: what does a crane look like? And previous methods have serious issues. The first we're going to talk about is polysemy. And this goes back to the example of the crane. I love cranes a lot. So you have the issue of bird crane versus construction crane. And when you have just crane, as we have in a lot of these data sets, you're not sure what someone means, right? There are other examples like metal nail versus fingernail, or baseball bats versus normal bats. When you have labels that use words like this, there is always going to be some level of ambiguity because, I mean, words try to do a good job, but they are not perfectly expressive. So what is our method? We start by trying to map the labels to the concept. So we have a class like dog, and we want to map it to dog in a semantic knowledge base. And what this does first for us is that it removes ambiguity almost completely, because now that we have dog, we know that we are not referring to like the dog tool or something like that. And what this allows us to do on the second level is that we can retrieve semantic knowledge about the concepts, such as definitions, alternative usages of alternative terms and examples. Okay, so the second phase of the method is normal prompting. I'm going to call it normal prompting because there's another kind of prompting we're going to use, which I can't wait to tell you guys about. But we use the retrieved semantic knowledge to prompt a large language model. And we see here that we have dog, which is mapped to dog. We use this information to prompt a language model. We actually try multiple and it performs, we see good performance across all. And we are able to get this visual description at the end. So I'm going to speak about another set of issues and talk about how we fix them. So we also have the problem of semantically similar concepts. So we have the example of an alligator and a crocodile. And until very recently, I didn't know the difference between them, but I'm going to tell you guys. So an alligator has gray skin and it has a round snout. And a crocodile is green and it has a V-shaped snout. But I think I wouldn't blame you a lot if you aren't able to distinguish these two things. And models have similar problems. And what we noticed when we worked with just the normal prompting was that there were a lot of false positives for a lot of these similar looking classes. Of course, that's understandable, but it's something we seek to minimize. So how do we fix this? We propose contrastive prompting. And here we want to traverse the semantic network to find the most similar concepts, for example, alligator and crocodile. And we want to prompt a language model to generate contrastive descriptions for alligator that highlights its differences from a crocodile. So this image sort of succinctly puts what I just said. We ask a language model what makes a crocodile different from an alligator, and it gives us these texts. And what we find out is that when we have things like this, they sort of, again, bias the model, bias the image model towards what we actually mean. So what are our data sets? We have ImageNet, which has 1,000 classes, 50 images per class, CFAR 10 and CFAR 100, which have 10 and 100 classes, 1,000 and 100 images per class. And we have STL10, which is specifically for unsupervised work, and 10 classes and 800 images per class. And what we want to do is that for each of the classes in these data sets, we want to produce visual descriptions and sort of evaluate the quality of all our visual descriptions. So experiment 1. Here we want to produce an ensemble of visual descriptions for each class. And what we mean by ensemble is that for each class, we want to produce, say, 50 descriptions, encode them and find an average representation of those things. And then we use these visual descriptions for zero-shot image classification. And zero-shot image classification, as opposed to normal image classification, here, the set of classes that we are classifying based on are dynamic. So with zero-shot image classification, I can say today that I want to classify a dog or a not dog, and the next day I want to classify a cat, a hot dog, and a rabbit, or something like that. And the metric here is top 1 accuracy. So the previous methods for this, I've spoken about some of them in the past. What's been done is that you plug like a class label into a fixed template, and you have something like a photo of a crane, and the template ensemble, you have this ensemble of fixed templates that you insert the label into, and with tuple, you simply prompt instruct GPT and sort of sample multiple descriptions from that. Sorry. Yes, so our results. We see that the baseline performs not great as we expect. Template ensemble performs decently well for something that is as raw as it is. Pupil performs well. VGloss without contrastive performs just around the ballpark of pupil, and VGloss, which is our full method that has the contrastive prompting built in, performs much better than all the other methods. And I think this alludes to how important the contrastive prompting is, because it's able to help us to distinguish things that would otherwise be easy errors that these models fall into. So I'm going to talk a bit more about our results and just reiterate how important focusing on visual attributes with precise and expressive descriptions is. So we see that that helps us a lot. Using the semantic knowledge base is able to sort of completely disambiguate whatever concept we're talking about. Like, we don't need to ask what kind of crane it is when we have it already marked. So a knowledge base and contrastive prompting is very important. And we can see this example of alligator and crocodile again. And we see that with the normal prompting, it sort of gives us similar things for both of them, right? And it's kind of difficult when we have these things to produce representations that are sufficiently distinct for each of the concepts. But when we have our contrastive descriptions, which focus on sort of differences between these things, we're able to understand these things distinctly in a better way. So our second experiment is data set construction. So we ask ourselves, how do we produce a top description? So not an ensemble, just a single description, and see how good it is when we focus all our efforts into producing one single description. And this leads us to a new data set, right? And we can compare this data set with something like WordNet, for example, which uses just descriptions or something like that. And what we want to do now is that we want to evaluate our data sets. We want to ask ourselves, is this data set useful or is it not? And what we do is that we evaluate it on text to image generation and zero-shot image classification. So the zero-shot image classification here is a bit different from in the past, because in the past we used an ensemble. Here we just used like a single description. But the metric we use here is inception score, which simply measures the quality and diversity of generated images. So here are our baselines. First, we have WordNet's glosses or definitions, which just it's just a definition of what the concept is. And we have this modified gloss, which sort of adds like a prefix here. And this actually helps a lot. And we have the baseline, which is simply a photo of it. And when we generate images with these modified descriptions, we see that the baseline performs reasonably. Just using the gloss, in fact, performs worse than the baseline. So it's really bad. The modified glosses perform decently well, but our method performs best because we sort of focus on the visual attributes, like I said. And here we see that our data set is in fact not completely useless. So,
Oh, sorry.
yeah, go ahead.
What is the task here? Image generation. So you generate an image, and how do you judge whether it's good or bad?
So we do inception scores. So what inception scores are, so you put an image into Inception X, which is like a CNN from some years ago. People use it because like right now because it's like standard. So you put it in there, you get the logits from like the second to the last layer. And what you do is like you compare the probability distribution of that and what you would expect to be some sort of like ideal distribution. So what you want to do is that you want to have many images that sufficiently describe a single thing. So you want to have an image of a crane, a bird crane that actually looks like a crane, not like sort of a crane, a construction crane and a bird crane. And you want to have like high quality images. You want to have many images of different things that are all high quality.
So you generate multiple images for a given prompt?
Yes, it's multiple images for a given prompt and multiple images for each concept. So I want to discuss this a bit more. So this is an example of us using our prompts to generate images. We have the example of a brambling again, and we see that when we use the more visually grounded description, as opposed to Eurasian finch, we are able to generate a much better image. So we see the similarity scores between these two images and this sort of anchor image. And we see that it's much lower here than it is here. And this sort of provides further evidence of the effectiveness of our method. So what's the main thing I want you to take away from this second project? Again, concept descriptions that focus on visual attributes improve zero-shot image classification and generation. But more importantly, you are able to reliably produce these descriptions just with a semantic knowledge base and a language model. The minor takeaways here are that semantic knowledge bases are useful for differentiating similar concepts, as we showed in the alligator crocodile case, and they are also useful for disambiguating polysemous class labels, as we showed in the crane case. And the combination of language models and semantic knowledge bases is synergistic. We see that previous methods that used only language models performed worse than our method that used both a language model and a semantic knowledge base. So in summary, our contributions are first, visual descriptions. We automatically produce precise and expressive visual descriptions with language models and semantic knowledge bases. And you can see an example of that here. The second contribution is that we use contrastive prompting and show that it reduces false positives. You can see an example of that here again. And we produce a new data set which outperforms alternatives. And we can see that here. So, final takeaway. We show that visually grounded descriptions help in multiple vision language tasks. The tasks here are visual word sense disambiguation, zero-shot image classification, and zero-shot image generation. And we can see that our hypothesis has been confirmed. So thank you.
Yeah. I forgot. How were you ensuring that these descriptions were visually grounded? Like, is it possible to? Can you also give an example of a description that's not visually grounded?
Yeah. So what we do is that we few shot prompted essentially. So we have a few examples of descriptions that are visually grounded, and we prompted the language model to generate a last one that is visually grounded as well.
Or WordNet has that?
No, that's not WordNet. That's the we prompt with data from WordNet, but the prompting is solely with the language model.
Oh, in the prompt you say, ChatGPT, I need visually grounded.
No. We don't do that. Well, we few shots. So we show, an example of that would be, I have like dog, and I say a dog is a furry mammal and so on. Then I want a visually grounded description of like a bat. Then I add that, so it gives me a visually grounded description of bat.
In context then.
Yeah, exactly.
I see.
Yeah.
And what would be a description that is not visually grounded?
So something like Eurasian finch, I mean, that's technically what a branding is, but it doesn't tell us anything about what it looks like, right? And that doesn't help vision language models a lot. Thank you for your question. Yeah, Abhishek.
Yes, could you remind me how the polysemy was resolved? Like, I would think that if I as a user prompt the model with just the word crane,
Mhm.
it makes sense that the model gives me examples of both, right? Because it doesn't really know what I want.
Yeah.
So, so what are you doing to resolve it? Like, how are you using the knowledge base to?
Yeah, I'm going to go to the slides that show this. But what we do is that we do a mapping, right? And when we do this mapping, we are able to get like map a word essentially to a concept, and we get all this extra information that sort of makes it very hard for us to not understand what this is.
But if the class is the crane, then which one would it point to? Would it point to like the bird crane or the construction? Like
Well,
WordNet would have like descriptions of both of them, right?
yes, exactly. It will have descriptions of both of them. And in fact, the reason why we choose ImageNet is that ImageNet is sort of based on WordNet, and it's easy for us to do that mapping.
Right. So now crane is mapped to both of these concepts. So then how does that help generate an image of a crane of a particular type?
So when that happens, what we can say is hold on. Where's the slide? Okay, I'll just go to the first one. So what we can do here is that, I mean, this is not the exact prompt, but I think this is the best example within the slides. We have crane, and we sort of map it to the semantic knowledge base, do our prompting. Then we generate something like construction crane is the machine used to pull up heavy loads for construction. And we put that into our text to image generation model, and we sort of see that we get a better image, even better than just having this construction crane, right? And the same thing goes for crane bird. The key idea here is that when we don't have more context that is relevant to the meaning we are trying to depict, the model gets very confused.
More questions? I'm interested in how to construct prompting. So in the example, we can see that you find two really hard case to distinguish each other, right?
Mhm.
So, but in practice, how do you do that? Like, you need to go through all the classes, like let's say like 1,000 classes of ImageNet, and do the peer-wise contrast prompting, or
Oh yeah, that's a good question. So we don't want to do something that big because that's like 1 million comparisons. We don't want to do that. So what we do is that we simply pick the top 5 most similar things. So in WordNet, there's this, since it's like a tree structure, we can say, okay, what are the things closest to this concept based on how many hops I have to make to reach the other concepts. So we can say that we're going to ignore things that take more than 5 hops and only distinguish things that are within 5 hops of each other.
yeah, I see. Thank you.
So here we would distinguish an alligator from a crocodile or some different kinds of dogs, but we wouldn't try to distinguish like a robin from a truck or something.
How much more expensive is this method? So I guess just using WordNet would be super cheap, like
Mhm.
LLM is more expensive. Give
Yeah.
a percentage, like 5% more expensive.
I don't have those numbers for you, but I suppose if you're using something like ChatGPT, it would be quite expensive. But the advantage is that you get like higher quality descriptions, and you only have to do the description generation ones, right? But for us, we used Cohere, which is like free.
Not computationally free.
Not computationally free. But there's sort of like some sort of trade-off here, right? We get descriptions that perform better empirically, but we spend more in computing power. I think that's a trade-off most people would be willing to